Okay, hello, and welcome to our next lesson in integrals. We are learning a new shortcut rule, and it is called U substitution. All right, U substitution. We use this rule to kind of work backwards from chain rule with derivatives. Okay, like right now we know how to work backwards from um, power rule, which is what we can do in number one. Um, number three is just taking the derivative. And number three is taking the derivative using chain rule. So I wanted that to be a warm-up so we can remember how chain rule works so we can work backwards from it. Okay? Down here in warm-up, this is just doing a couple more power rules and exponential rules. And then number four is taking the derivative again using chain rule. So try these four warm-up problems and we'll talk about them in class. But let's go ahead and jump into today's notes. Okay. All right, first things first. I'm going to write out in steps what U substitution is, along with an example. I think this is important to write out. Honestly, you can skip to the end of this if you want to just write down the steps, but I'm going to explain it as I go, how U substitution works with integrals. Okay? So the example I'm going to use to teach this is 5e to the 5x dx. Okay. Now, originally, we cannot take the integral of this because we have this inner function here, 5x. We don't really know how to take the integral yet, but we have an inner function. Okay. So let's go through this in steps. Number one is you want to ID your inner function. Okay. You want to ID your inner function, and that's what we're going to make u. So in this case, our inner function is 5x. We're going to let u equal 5x. Now, number two, we're going to do all this in scratch work over here to the side. Is we're going to figure out, we're going to find du over dx of our inner function. So we're going to take the derivative of this with respect to x. Okay? And then we're going to solve for du or dx. You'll see what I mean. Let's do it right now. Okay. Okay. So we got du over dx equals, and the derivative of 5x is just 5, just 5. Right? We're taking the derivative of x, and the derivative of 5x is just 5. Now, what I mean for this part right here, for solving for du or dx, that means getting du, most of the time du by itself. So we're going to multiply both sides by dx. Let me show you what I mean now. So I got du equals 5 dx. Okay. Now, what we're going to do now is the actual substitution part. We're going to get everything in terms of u. Okay. So we're doing all this in step 2 here. So look at this. 5 over dx is the same thing as du. So what I'm going to do here is, if you look over here, there's 5 and dx. I'm going to substitute that in as du. So what I have here is e, and instead of 5x, I'm going to plug in u in for 5x. So what I have is e to the u du. I got rid of the 5 and the dx and made that du. I got rid of the 5x and made that u. Okay. So what we're talking about in step 2 here is being able to take the derivative and substitute everything out. So now we got a completely new problem where everything is in terms of u. And the whole point of u substitution, doing the scratch work over here in number 2, is that it makes the problem a little bit simpler to solve. Okay. So in my third step, I'm just going to take the antiderivative. I'm going to be able to, I can do the rest of the work. Okay. And the antiderivative of e to the u is just e to the u plus c. Okay. And then in step 4, we just sub back in u whatever the function was. We just substitute back in for x. So if I do that, I got u as 5x plus c. And that's my integral. Now, if you want to do an additional step, I don't do this often, but we can always check our work here. The derivative of e to the 5x plus c, well, of e to the 5x is e to the 5x times 5, and the derivative of c is 0. And if we look at the very top of the problem here, that's what we started with, 5e to the 5x. 5e to the 5x. Okay? So, it's all about identifying the inner function, setting it equal to u, and setting up a new problem. And I got a lot of examples to practice. Let's do this. Okay, let's do, I want to do this one. I want to do 8x cosine of 4x squared dx. Okay. Now, whenever you're taking an integral, you can't just do basic cosine rules. You got a bunch of other stuff going on here. What you need to be able to do is recognize what your inner function is. Okay? This is the steps that we're doing over the scratch work. What I did in that last example, I do over in the scratch work. You start by letting u equal something. And sometimes you might get it wrong from the start. And how you get it wrong is when you plug stuff back in, you can't integrate. You might have to redo this part. So never give up. Okay? The inner function here is 4x squared. Okay? So then if I do du over dx, the derivative of this is 8x. And then solving by multiplying both sides by dx, I get 8x dx. Okay? So I took the derivative and got du over dx by itself. Now, to be honest with you guys, I skip this middle step a lot, and I just go straight to here. The derivative of u is du, derivative of 4x squared is 8x dx. I skip this middle step a lot, and I encourage you to do the same thing. Just know that it's du equals 8x dx. Now, if we did it right, a lot of times, we'll be able to identify this piece in the problem. For instance, here's 8x, and here's dx. So I can substitute both those values out for du, and I can substitute out the 4x for u. So my problem in terms of u is just going to be cosine of u du. Remember, this part right here substitutes out as du, and I plugged in u for 4x squared. So I've simplified down this problem a lot. Okay? And now I can integrate cosine of u to just be sine of u plus c. And if I substitute everything back in for u, I got sine of 4x squared plus c. So that's my answer. Now, if I want to check that answer, think about what happens. If I take the derivative of this, that's cosine of 4x squared, and then multiplied by the derivative of the inside is 8x. And compare that to the top, okay? Like, this is what we let u equal. The chain rule, what's coming on the outside, is what's going to substitute out. That's kind of how u substitution works. It's working backwards from chain rule. I want to do one more example before we move on to the written examples. I want to do this one real fast. Let's do the integral of 7 secant squared 2x dx. Okay. All right. Look how this one works. The inner function here is 2x. You can't take the integral of secant squared 2x without taking out the 2x. So we're going to let u be 2x. So then du is 2 dx. Okay, look. 2 dx. All right. Well, if you look in the original problem, there is no 2 dx. Okay. So simply put, if I'm trying to substitute out the dx, let's move the 1/2 to the other side here. We got 1/2 du equals dx. So what this means is wherever I see the dx right here, I'm going to plug in a 1/2 du. Okay? And then what I'm left with is the integral of 7 secant squared of, instead of 2x, u. Okay? So now you see we got everything in terms of u. Now to make my life a little bit easier though, I'm going to take the constants out. That's one of the rules of integration is I can take the constants out. I can take 7 1/2 out, or 7/2, and I'm left with secant squared u du. Okay? So if the constant, the point of this is that the constant does not substitute out at the beginning. Just move it over with the du and substitute all that in for dx, and then you can take the constant out. All right, the integral of secant squared is just going to be tan of u plus c. And then plugging back in what u was, remember that u was 2x, I have my final answer. Okay. Very nice. All right, let's keep going. All right. Taking the integral of y cubed square root of 2^4 plus 1 dy. We got a lot of stuff going on here. That's not terrible. Look at the inner function. The inner function is what's being plugged into the square root. Okay? We're going to let u equal 2y to the 4th plus 1. So then du equals 8y cubed dx. That's my scratch work over there. Now, if you notice, we got y cubed and we got dy. So here is y cubed, or I'll put dx, I'm sorry, I should have put dy. We got y cubed and dy right there. Okay. So because there's no eighth, I'm going to bring the 8 over here. I'm going to say 1/8 du equals y cubed dy. So I'm going to substitute out this for 1/8 du. So this and this are going to go away because I'm plugging in y, or I'm plugging in 1/8 and du. Okay, I'm going to go ahead and bring the 1/8 out as a constant. Instead of the square root of that crap on the inside, I got u. And instead of y cubed and dy, I got du. If you wanted to plug the 1/8 in first and then pull it out after just so you can see it right, that's fine. But I always bring the constant out when I'm doing it. And this isn't terrible at all. This is just 1/8. Remember that this is the same thing as u to the 1/2 power. So we're going to add 1 and divide. So if I add 1, it's now u to the 3/2. And if I divide, that's 2/3. Plus c. And now all we do is just plug back in what u is equal to, and we're pretty much done. So that's 2/24. U was 2y to the 4th plus 1, and then raised to the 3/2 powers plus c. So if you want to simplify, maybe you can say 1/12, 2y to the 4th plus 1 to the 3/2 plus c. All right? Not bad. Okay, here's another type of problem to do, use substitution. If you have, I'm going to go ahead and tell you a little trick here. If you have a rational, and you have a difference in the rational of a degree of 1, so I'll write it this way. If your numerator's degree is less than your denominator's degree by 1. Okay, that's a good indication. It's not always true, but a good indication that you're going to be dealing with the natural log of x. Okay, so what you do is you want to let u equal some quantity. Usually it's the more complicated one, because when you take the derivative of the more complicated one, it looks like the simpler one. Well, let me explain. So I'm going to let u be 1 plus x squared. So du equals 2x dx. Okay, look at this. So I got the x dx and I got x dx right here, right? I got the bottom that I'm going to let equal to u. I'm going to let this top part be equal to 1/2 du. I got to get the 2 to the other side. So this is going to be equal to 1/2 du. Okay. So if I set this up in terms of u, I'm going to go ahead and bring the constant out. So 1/2 comes out. The top part here, x dx, becomes just du. So I got du on top, and on bottom I got just u. Okay. Now a better way to write this so you don't get confused is I always write du out to the side. I always write the du out to the side. So I just have 1 times du right here. Okay. And then we know the integral of 1 over u. ln absolute value of u plus c. And then we just plug back in what u is equal to. We're done with the problem. Okay. So again, a difference in degree of like 1 on top and bottom. The denominator is greater than the numerator by 1 degree. Usually we can let the denominator be equal to u, and then it's going to turn out we can do natural log. So that works out pretty nice. Okay. Let's try another one. Now, this looks like a huge mess, but look what we're dealing with here. You got a function being plugged in to a power of 4 on the bottom. You got a power of 3, you got a power of 2. I bet that the inner function, and sometimes you have to mess around with it and guess it sometimes, but I would bet that the inner function here is all that inside the power of 4. So I encourage you to stop these videos at the beginning of each of these problems and try them, but I'm going to let u be x cubed plus 3x squared plus 9, and then du equals 3x squared plus 6x dx. Okay, here's the dx. Now x squared plus 2x, compare that to 3x squared plus 6x. Looks pretty dang close. It's off by a factor of 2. What if I do this? What if I take a 3 out? I'm left with x squared plus 2x. Do you see now this matches up with this? All right, so I'm going to bring the 1/3 over. And I got x squared plus 2x dx. So this, or what I have circled here, is equal to 1/3 du. And what I have inside the parentheses here is equal to u. So what I'm left with is the integral of, okay, the 1/3 I'm going to take out. And this whole top part is equal to du, but I'm just going to say 1 and du off to the side. And on bottom, I have that quantity is now u to the 4th. Okay. So I got everything in terms of u. It's a lot simpler of a problem. And what I'm going to do now is just integrate it, doing our power rules. Okay. Remember, u to the 4th on bottom is -4 on top. And that's just power rule. I'm going to add 1 and divide. So I got 1/3 integral of, if I add 1, it's -3, and divide, it's -1/3 u to the -3rd power. Oops, and I don't know why I put the integral symbol. I'm sorry. Okay. The integral is, again, -1/3 u to the -3rd plus c. And I can combine the constants together. I can say that's -1/9. And then how about 1 over u, which was x cubed plus 3x squared plus 9, all raised to the +3rd power, plus c. So now it's back in terms of x. The u is gone. The u is just a tool to help us simplify the problem to 3. And we get it back to x at the very end. All right. I got a few more. Let's see how much we can get done. Okay. Now, let's talk about u substitution with definite integrals, meaning that we have a bound. Okay? Now, I encourage you to pause the video and try to figure out this one on your own. So I'll encourage you to do that now. But the u, in this case, 9 minus x squared. That's the inner function. So let's see what happens. Okay. So du equals negative 2x dx. Here is the x dx. We got a dx and an x. So if I bring the negative 2 to the other side, I got that x dx becomes negative 1/2 du. So what I'm left with is the integral of 0 to 3. I'm going to bring the negative 1/2 out. These things I have circled here become du, and I'm left with the square root of u to the du power. Just brought the negative 1/2 out, left du on the inside, and I got the square root of u. Everything's in terms of u. Okay. Now, if I integrate, okay, and something I want you to do for me, I should have said this at the beginning, don't put the bounds just yet. Okay, and I'll explain why in a second. Okay? Because there's two ways to do this with a definite integral. I'll teach you both. I stick with one way, but I'm going to teach you both. The first way is probably the way you'll make more sense to you, is x bounds. But the other way is much quicker. Let's go ahead and integrate this. Okay? So to integrate this, it's negative 1/2. The integral of u to the 1/2 is 2/3 u to the 3/2 powers. And it's not plus c because we're going to be plugging in some numbers. But before I can plug those numbers in, I got to get it back in terms of x. So what I have is negative 1/2, 2/3, and then the x was 9 minus x squared to the 3/2. And we're going from 0 to 3. Okay. All right. And then you just plug 3 in, you just plug 0 in, and you go on with your life. I like to bring out the constant when I'm doing this. So like I like to take the GCF out. Like this would be like, so negative 1/2 times 2/3 is negative 1/3. And then what I have left on the inside is plugging the numbers in. So the first one's going to be 9 minus 3 squared to the 3/2 minus 9 minus 0 squared to the 3/2. Okay. And then I can multiply all that. It just prevents me from having to write negative 1/3 twice. All right, so we get negative 1/3. 9 minus 9 is just 0. And then minus 9 to the 3/2 is actually 27. So my final answer is negative 27 times negative 1/3, which is positive 9. Okay. That's called x bounds. So that's literally taking the integral, doing u substitution, which is what we did, plugging u back in, and then doing the process. Okay. Now, personally, I like u bounds. This is the way I tend to do it in the future. Same thing, really. So I'm going to pick back up where I left off right here. Okay, but I got negative 1/2 integral of u to the 1/2 du. Now the thing is instead of plugging back in 3 and 0 or plugging back in an x at all, a cool trick is that if you're doing a definite integral, you don't need to go back to x at all. You can just leave it in terms of u. You see, the thing is on the left, we went back to x because our interval was in terms of x. This is x equals 3 and x equals 0. But instead of going back to x, what if at the very beginning I churned my interval in terms of u instead of x? Okay, well remember, u is equal to 9 minus x squared. So what if I plug 0 into that and 3 into that to get a new interval in terms of u? So for instance, if I plug 0 into that, it's 9. If I plug 3 into that, it's 0. So now that everything's in terms of u, I don't have to go back to x, and I can just keep it in a simplified version. All right, so watch. All right, first of all, we know that the integral is 2/3 u to the 3/2. Now, instead of going back to x, what if I just leave that in terms of u? It's going to give me the same answer. but without less complicated equation. So look what I mean. We got negative 1/3, and then times 0 to the 3/2 minus 9 to the 3/2. And look what I get. Negative 1/3, negative 27, and I get the same exact answer as below, but I think it takes a lot less steps because you're not having to plug back in x at the very end. Okay? You can leave it in terms of u because it's a definite interval. This only works with definite interval. If I'm just asking for the function, you got to go back to x. Okay. How much time do I got? Minute 25. Yeah, okay. Maybe I can try. I'll do one more. I'll do this one. And then I'll leave, well, that only leaves us one more for class. Okay. Yeah, I'll do this one. Now, it's a definite integral. So I'm going to do u-bounds. I think u-bounds is the way to go. Okay, what's the inner function here? Well, you have two options. It's either ln of x or x. You can try either one. I would encourage you to stop the video and try either one. But you got to ask yourself, which one's going to simplify it down more? Like, which derivative is going to be more applicable? What happens if I let it be ln of x? Then isn't du 1 over x dx? And hot dogs, look at this. dx and x. dx and x. So I can let this be u, and I can let this be u. So this is du, and the top is u. So what I really have is the integral of u du. That's it. Now, instead of using 1 and 5, go ahead and get those in terms of u. Prevent us from having to go back to x. Like if I plug 5 into the u equation, that's the ln of 5 on top. And on bottom is the ln of 1, which the ln of 1 is just 0. So look what we got. The integral of u, we know, is 1/2 u squared, and we're evaluating that from 0 to ln of 5. And we don't have to go back to x, because I got my integral in terms of u. So this is just 1/2 ln of 2, or sorry, ln of 5, I don't know why I said 2, squared, minus, I always like to leave the 1/2 on the outside, 0 squared, which just simplifies down to 1/2 ln of 5 quantity squared. And I guarantee you, if you did this as x bounds, if you decided to plug x back in at this point and leave the interval from 1 to 5, you get the same answer. All right. Well, I encourage you for this last one. It is a definite integral. I encourage you to try u-bound on this one, and I encourage you to try it on your own. Look for the inner function. What could be the inner function? All right. So try that one. We'll go over it in class, and good job, guys. Talk to y'all soon.